The name of this video is Work and Potential. Consider a single point-like charged particle with charge small q in space. This is the location of small q, our source charge. From Coulomb's law, for a single charge, we know that the field, the electrostatic field E associated with it, is central with a spherical symmetry. In 2D, the Faraday field lines are therefore radially directed, and you need to think about these field lines as always in 3D with spherical symmetry. But in 2D, they look something like this. This is one field line radially directed for E, and similarly, there will be many other field lines. And so on and so forth. This is our charge small q, our source charge. We know that for such a Coulombian type electrostatic field, the electrostatic potential, a scalar function V associated with it, mathematically can be written as V of R. Let us choose, as always, a spherical coordinate system where the radial axis, for example, coincides with this field line here. I just sketched it a little bit off to clearly distinguish it from the field line, but effectively the same. So this point coincides with the origin of such a spherical coordinate system where I only show R, I do not show theta and bar phi. But again, you need to think about it in 3 dimensions. So in this case, the only variable for the electrostatic potential, as we know from a previous video, is small r. And the electrostatic potential function is given by 1 over 4 pi epsilon naught. Q, our source charge, divided by small r. Great. So let us suppose to pick a point here on this field line. Let us call this point capital A. If we fix ourselves at this point capital A, which is at a distance RA from the origin, so this distance here is RA, and we compute the electrostatic potential at that point, and note that this electrostatic potential is a specific one where we have chosen the arbitrary constant C to be equal to 0. That is, this is a green function for normal conditions. Well, in this case, the electrostatic potential is constant at that value RA. And so we can sketch it in 2D as a circle centered in small q. So the circle will look like this. Okay, this is a circle centered in Q, associated with the potential at point RA. Note that, in general, this is actually a 3-dimensional surface, it's a sphere, and this sphere is called an equipotential surface. Okay, note that at each point on the equipotential surface, let's say this point here, happens to be normal So it forms a 90-degree angle with the fill line at that point. Okay? So at this point, the equipotential surfaces are normal to the fill lines, as there. Suppose to take another point somewhere here, and let us call this point capital C. In this case, this distance is RC. So in this case, if I fix this electrostatic potential at RC, it's also constant, and will identify another sphere, another equipotential surface with a different value, concentric with the first one. So also here, we will need to sketch a circle all around. I will stop somewhere here, but it's intended to go all around, having a Q as a center. Okay? So O is the center of this other circle. They're concentric. This is another equipotential surface. All right. Obviously, on the equipotential surface, everywhere the potential is the same. That is why it's called equipotential. So suppose now to consider a closed line gamma, which goes from point A to point B here, in this direction, from point B to point C in this direction, from point C over the arc in this direction to point D, and from point D back to A in this direction. This line, we call it a line gamma, and is a closed line. We already investigated a similar line when we discussed the rotational property of the electrostatic field, which obviously is connected to the concept we are analyzing here. We already know that there is no contribution to the work on the arcs AB and CD. See a previous video. What I intend to calculate in this case, in this video, is once again the work, which we again already calculated previously, to go from B to C, and I want to connect this concept to the concept of electrostatic potential V for this very simple example. So let us compute the work W along gamma to go from B to C, okay? This vector here, this segment BC. So this work we know that is given by the value of the test charge Q0, which I place on this line and I move it, is this charge Q0 times the line integral from, let us specify this integral already with respect to this coordinate system OR, and so we go from RB, which actually happens to be the same as RA. These two segments are exactly the same length, so let us call it hereafter just array for simplicity. So we go from RB, which is actually array, all the way to RC. This will keep calling RC. Of what? The electrostatic field. Q0 times the electrostatic field is the force, which we need to integrate to get the work, 1 over 4 pi epsilon naught, times the charge Q, which is the source charge of the field, divided by R quantity square, a Coulomb type electrostatic field, in direction UR, and this we need to dot it with UR dr. All right, and specify this UR here, better subscript. UR dr. Great. All right. So let us compute this work. Let us move up here. So from here, this work is given by Q0. These are all constants of integration. What is the integral of 1 over r squared? That's minus 1 over r, minus 1 over r, okay? So let us remember this minus 1 over r. UR dot UR, of course, is 1. So we are going from array to RC, between these 2 points, from array, which is the same as RP, to RC. So we're going from array to RC, but with a minus 1 over r. And so the result of this work will be Q0 times Q divided by 4 pi epsilon naught, these are all constant of integration, minus 1 over r, minus 1 over r from a to c, so it's 1 over r from c to a, so it's 1 over r from c to a, which means it's going to be from c to a is 1 over ra minus 1 over rc. And again, the reason why it's inverted is because this integral gives me, as we know, this integrand gives me minus 1 over r. Okay, so I invert these two limits of integration accordingly. So effectively from c to a, so I need to do a minus c. And remember that a is smaller than c. So clearly here, it so happens that Ra is this distance is smaller than Rc, definitely smaller than Rc. All right, this quantity which I'm about to highlight in yellow here, multiplied times Q naught, this is nothing but Q naught times the electrostatic potential V. At what point? At point Ra. But remember that Ra is nothing but Rb, so let's call it a point B. All right, so this is the same. This is the same as Rb. So don't get confused. The same is B. It's B is the first point minus the electrostatic potential V at the end point, which is C. Is this quantity positive or negative? Obviously, since Ra or Rb is smaller than Rc, this is a positive quantity. Great. So this means that when I go from B to C, along this line, I'm falling along the field line, which means the work due to the field forces so the field forces are the forces, this is the only force generated by Q due to field forces, in this case the only force, the field force, is positive. These are also called internal forces, to distinguish them from external forces as will become more apparent in a few minutes. All right, similarly, if we now, of course on CT there is no contribution, if I go from D back to B, in that case the work along gamma to go from D back to B, this will be equal to Q naught, the bracket electrostatic potential at point D, which is the first point where I start, minus the electrostatic potential at the last point A. Again, since this radius is larger than this radius, when I invert them, in this case, this quantity is smaller than this quantity. And again, the reason why I go from D to A is because there is a minus in here. All right, so in this case, this quantity is less than 0, is negative, okay? Which means in this case, on this segment here, I'm rising along the field lines. So in order to rise along the field lines, what actually you need to do, I actually believe that rising is probably with an A. Luckily, I already passed my English test, so I don't need to check the spelling of that word. And so, in other words, to go in this direction, to have a negative work, I must go against the field forces, okay? So I need to use, in this case, some external force to climb up in this direction. We'll come back to this in a minute. All right. So, and the work, of course, is negative, so I'm rising in that direction. Now that we have this connection between work and electrostatic potential, it is also worth mentioning that the units, the SI units for V, for the electrostatic potential, the units are volt, capital V, or in short, volt, which somehow comes from the Italian physicist Alessandro Volta, but somehow the A got forgotten. All right. So to conclude, in this panel down here, let us generalize a little bit this concept which we have seen here for a very specific case of this line ABCD, which is a very simple line on this with these two arcs, etc. So let's suppose, more in general, let us suppose to consider a generic line gamma with any direction, which has any shape you want, that goes from a point, let us call it capital P1. This is the beginning of the line. It goes in some direction. Let's say this is our gamma to capital P2. All right, and suppose that again, I have somewhere in space a charge, a point capital Q, a charge small q, which generates, is the source that generates the field. I put a test charge on this line gamma, and I want to move from capital P1 to capital P2 with a test charge Q naught as always. All right, in this case, for example, let's pick, let's say this point here, my test charge Q naught, let's say that is located at this point here, which is a generic point capital P on the oriented line gamma. So in this case, from Coulomb's law, we know that there will be, let's say, a force, if this is all positive, a force F, this is the force F, I of the internal force. It is an internal force. This is the force due to my search charge, which goes in this direction again, according to Coulomb's law. So this is the force on Q naught at that point capital P. All right, so the experiment, the Gedanken experiment, the thought, which means in German is a typical expression in science, the thought experiment I want to do is to move a particle along a line. So how do I force it in this Gedanken experiment to move along this line? Well, in order to force it, I need to apply a counter force, because obviously if I leave it like this, it's not going to follow this line, it's going to accelerate in this direction. So I don't want that. I want to have almost zero acceleration. That is just a tiny bit velocity that allows me to follow this line. So to do that, I need to use an external force which is almost the same and opposite, but perhaps a little bit different, with a little bit of an angle. So this is a little bit of an angle, okay, compared to that. Imagine here a little bit of an angle, okay? So this external force F E, the external force, okay, E for external, is almost equal and opposite to Fi, the internal force. This little difference, I need it to have a tiny bit of a velocity, but basically the acceleration at each point, capital P, is approximately a zero vector, okay? But yet there is a little bit of a velocity that allows me to follow this line gamma, okay? This is called a quasi-static transformation, when this acceleration is very, very tiny, okay? All right, so under these conditions, so we need to remember the whole discussion here is we have two types of forces, the internal force generated by Q, and my hand, which is an external force which counteracts it, but a tiny bit, I need to have it a tiny bit different so that I can actually follow the shape that I want. So my hand allows me to follow the shape I want in a quasi-static fashion. So if we do that, in general, it so happens that the work W along gamma to go from point 1 to 2, definition of work is going to be to Q naught. Line integral on gamma from 1 to 2 of E, the electrostatic field, EI if you really want to be picky, dot TDL. This is the work we need to perform. Now we know that the electrostatic field is a conservative field, therefore this can be rewritten as a minus Q naught, the integral from 1 to 2 of the gradient of V, the electrostatic potential, minus the gradient of V is E. This is a vector. We know that this quantity is a vector. This, I need to dot this vector with TDL, which means I need to project it along TDL. This projection actually leads to what is called the directional derivative, the directional derivative of B, and so if you rewrite this down here, let's remember the minus sign, so this becomes effectively in this curvilinear abscissa, which is along gamma. So the curvilinear abscissa means that if I start, let's say, from the origin here, and I go along this line until I reach the point capital P here, this quantity is L, okay? So it's an abscissa, so it's a generic curvilinear coordinate that I'm using here. So I need to perform, let's remember the minus sign, so let's already use it. Okay, actually here, let's still keep it outside, and we will, in the next step, we're going to actually use it. So this is going to be minus Q naught, the integral from P1 to P2 of what? Of the partial derivative of V with respect to L. I'm projecting the L. But clearly, this is a state function. We already know that this is a state function, so also its gradient is a state function. It does not depend how we go from 1 to 2. It only depends on the limits of integration here. And so, finally, using this minus sign, so we know that here the L and the L basically cancel out. So we end up having the integral of a dv, okay? So the integral of dv from vector calculus, from actually calculus, will be v at P2 minus v at P1. But with the minus sign, it's going to be Q naught times bracket V, the electrostatic potential, at point P1 minus point P2, minus V at point P2. And again, why do we go from 1 to 2? Because there is this minus sign here. So this, I really want to stress it. People do lots of mistakes with this. Because of this minus sign, effectively, I go from 1 to 2. From the beginning to the end, not from the end to the beginning. Okay, like this. All right. So this is the work which we started to calculate from E, the internal electrostatic field, and eventually we find it from the perspective of the electrostatic potential. Okay, Vp1 minus Vp2. We will use this soon. And this one is the work, to be completely precise, is the work due to the internal forces. So it's the work due to the internal forces. As it turns out, when we will define electrostatic energy, the electrostatic energy is defined as the opposite of this, is the work of the external forces. So keep it in mind. All right, so to summarize this video here, in this first panel, here, we introduce the concept of equipotential surface, which is normal at any point of the field lines of the electrostatic field, in this case for a single point-like charge in space. We then use the definition of electrostatic potential, Green function with normal conditions at infinity, so capital C is 0, to find the work, for example, from B to C and D to A, and we found that this depends only on the limits of integration, obviously, as we already know, and is positive when I go from B to C, falling along the lines, and here I'm rising along the line, so it's negative. And here we distinguish between internal and external forces. And finally, in this second panel down here, we generalize from this specific line to any line, and by means of the concept of directional derivative, which is a projection of the gradient along the TDL direction. Okay, mind you that T here obviously is the tangent unit vector. This is T. Well, from this directional derivative, from calculus, I know that the work due to the internal forces in a quasi-static transformation is Q naught P1 at the beginning minus V at P2 at the end. That's it.